is Noel Khan with 8 Queens. I've been in the geospatial community for about 16 years, mainly as a developer and as an architect, so I tend to focus on capabilities. So I'm going to be talking about in a minute.
Yeah. So what's up?
Quick talk.
Yeah.
Okay, there we go. All right, automatic georeferencing. So the agenda is pretty straightforward. I'm going to focus mainly on the motivation because I think it's important to have a justified solution. There needs to be a compelling reason for whatever it is you're building, and then just problem, proposal, solution, roadmap, and I'll show you examples of the output. So, where do ideas come from? What I tend to do is look at the trajectory of technology, where it began, where it is now, and then extrapolate that into the future to get a pretty good idea of where it's evolving. And it's a good way to filter out fads. So I'm going to take you across this trajectory really quick. So we started with CAD systems, and that gave us the ability to just digitize a ton of data until it became unmanageable. We had thousands of files, couldn't really find things. It was almost as bad as having paper maps. And then you had limitations in the software. It just took forever to render things. And so we created geodatabases. And geodatabases basically created an index of all that content and stored it in a database. But the introduction of a database created the opportunity to add in business-specific metadata. Like if you were maintaining a parcel layer, you could add owner information, you could add real estate information. And the key thing is that in adding additional content, and in adding metadata, you actually enhanced the value of both data sets by creating that relationship. Then Desktop GIS was able to leverage that content, leverage the metadata to create subsets, and it also gave us spatial operators so that we could start looking at spatial relationships between our data. And some of the CAD guys might say, well, you could have done spatial analysis in CAD, but the thing is you would have had to have built a custom spatial analysis tool using MDL or something like that. It wasn't out of the box. Desktop GIS gave that to the end user. And I think that's an important philosophy that users should expect from their vendors. Expect your vendors to bring high technology down to the level of the common user. Why? Because you want people to be able to make more timely decisions rather than having to go up the flagpole, get a developer, and build something. And you see this philosophy reflected in Hexagon smart maps because they've given you hundreds of very complex spatial operators, but they've given you a visual design environment. You don't need a programmer. And most of the, participants, most of the finalists weren't programmers, and I think that's telling. So anyhow, Desktop GIS users, if you know any, they create tons of data, and they put it all over the place. So publishing it online addressed a data silo problem. And it also made that data available to a larger audience. So you had analysts outside of the GIS community start mashing data together and looking for relationships across data, and that was new. Today, in the era of big data, never mind my low-tech teleprompter there, with big data, we're trying to automate and simplify this process of looking for relationships within and across data. And so if we look at what insight can we get from this trajectory at a very high level, there was this huge expansion in data and then synthesis, some integration. It's kind of like the Big Bang. Analysis isn't the end game, synthesis is. At a low level, you could see that the synthesis began with simple data types like text and number, and eventually evolved to complex data types like geometry. I think the thing, though, is that most of these operators operate on the same data types. text and text, geometry, geometry. I think what's needed, if you extrapolate that trajectory, what's needed are operators that can operate on different data types. And that's what I'm proposing with automatic georeferencing. An operator that takes a raster image and a vector model and automatically georeferences the raster to fit the model. And usually the way this is done manually is you have to identify key points, and then you do a rough placement, and then you drill in, you do another set of key points, and continue to sharpen up the placement. So, how are we going to automate? It's pretty complex. It's a challenging computational problem because of the state space involved. A raster image is typically a small geographic area, but a vector model is typically seamless, and it's very large. I mean, roughly 5 orders of magnitude larger, like if you were to compare a map of a neighborhood to a map of the local municipality. And that makes it computationally intensive. This isn't something that you would really expect to do online. A related challenge, because of the computational complexity, is balancing the trade-off between performance and accuracy. And then there's also the issue of noise. I mean, it doesn't really make sense to try to combine 2 data sets that are identical. You're going to be combining data sets that are different in some way. I mean, if you think about aerial photography, if you think about cadastral maps, which are based on lines of ownership, and if you look at maybe tax maps, they all are different visualizations of the same underlying geography. They're different. So you have to deal with extra data in one data set that doesn't exist in the other, outliers, missing data, distortions. If you've ever looked at transit maps, those are usually like cartoon maps. So you have to deal with all these challenges. So again, the proposal is to create a smart map that automatically georeferences images. Is it even feasible? It is possible. There's a few simplifying assumptions, and in fact, I've already built a system that does just this, but it's batch-oriented. It takes a huge volume of data and then cranks away and georeferences maps. I think the benefit of porting it to smart maps is that it allows self-service for smaller volumes of data. And so now this service is available to people that I wasn't really catering for. It opens up a new market segment for me. So let's talk about scope. So everyone in the room's probably experienced a period at work where you were just spread too thin. What does that mean? You probably weren't performing very well. You were just getting by. You're trying to get past that busy time. I mean, algorithms are the same way. If you try to create one algorithm that does everything, the performance isn't going to be too good. What you need to do is create a very specific algorithm, a tailored algorithm for a narrowly defined problem, and you'll get good performance. And that's how we're going to address some of these computational challenges. So because of that limitation, because this is a 2-month contest, and because I can't really constrain the functionality, either georeferences or it doesn't, I have to constrain the input. And so the raster input will be limited to assessor tax maps that every single county in this country produces. There's about 3,000 counties in this country, and I estimate there's about 15 million assessor tax maps. That's about 20 terabytes of map chest capacity. Local governments aren't the only ones that use these maps. They produce them, they sell them, it's a product that they have, but I mean, it's used by a wide variety of people in real estate, farmers, because they get taxed based on what the crop they're growing on their farmland. The vector input will be limited to parcel layer that has metadata for taxation, because I can use the metadata to actually prune state space. So instead of trying to fit a map that's only 0.01 square miles against an 800 square mile area, I can actually trim it down based on the taxation metadata. So here's an example of the data. On the top there, you see an example of a tax map. And in the lower right, you can see there's an inset. And in the top right, you can actually see leader lines. These are all the variations that I was talking about that make it a challenging problem. Because if you were going to try to place this thing, that would be like an outlier, and it would throw your georeferencing off. So that needs to be handled. If you look at the bottom left, you can see on the top that there's very large parcels, but then on the bottom you see very small parcels for what looks like a condominium community. So to talk about the solution, automatic georeferencing is at the intersection of optimization and computer vision. There's an IEEE conference paper that details the problem and the solution. You could find a reference to that on my LinkedIn page. I know it's a shameless plug, and clickbait, but I need the traffic. But one thing I will talk about is optimization. So optimization is just like calculus. So if you can model this problem using some sort of mathematical expression, then all you have to do is take the first derivative of it to find the solutions. Well, you find extremal points, and then you take the second derivative to see whether those were minimums or maximums, and then it depends on what your objective function is, whether you're trying to maximize something or minimize something. But the problem with calculus is that it only works if there's no noise. And we're not assuming noiseless data, we're assuming very noisy data. So strike that, we can't use calculus. You could use regression, but regression usually gives you compromised solutions. And regression kind of chokes on 2D problems. It's been used on 3D problems. It just doesn't scale well. This is actually a 5D problem. You've got one parameter for X translation, Y, X scale, Y scale, and also rotation. So it's a hopeless case. So in keeping in the spirit of bringing high technology down to the common user, I'm using an artificial intelligence optimization technique called differential evolution. There's actually better techniques as far as accuracy, but differential evolution has the best trade-off between performance and accuracy. So, teleprompter, let's see. All right, so the current batch-oriented system, it solves one problem about every 10 minutes. And that's on a 32-bit single-core virtual machine. That puts it on par with human performance. I built the system into a VM so that I could scale it out. So if I get a large volume, I could just get a whole bunch of instances on Amazon EC2 and just spread it around. The problem is that it's a manual process. And one of the things that is attractive about Smart Maps is that it's already on Amazon Cloud, and it scales itself. All right. 10 minutes is pretty much forever online. No one's going to wait for that. So in the last couple months, I've actually found an alternative solution that can speed that up by an order of magnitude, and that's what makes this possible. Risks, there are risks. The technical risk is that in spite of there being hundreds of operators built into Smart Maps, it's possible that the operators I need to accomplish this aren't there. From a business side, it's really, really minor, but I'm wondering whether like a metered pricing model would work better than a subscription or an app purchase, but like I said, that's minor, so it's not a slam dunk. Let's see, roadmap. So the scope is limited for this contest, but what I'm working on is generalizing this solution so that it works with arbitrary maps. County governments are always telling me, well, I want it to work with this type of map or that type of map. Fine, I'll work on that. I'd also like to extend the system to work with different data types. So imagine instead of georeferencing an image to a model, what if it's a video to a model or any other permutation of different data types? And then the last bullet point there, that's the unicorn. If this can be extended to 3D, there's a lot of possibilities. These are examples. These are actual examples, but from the batch-oriented system, so that you can get an idea for the placement error. In general, I think I have that back here. Mean accuracy, 8%. Rotation error was the mean. Placement error was 28%. Scale error was 2%. So you can see that. Now, these maps are usually landscape. And you can see this one was rotated about 90 degrees. This one didn't really need to be rotated. This one was rotated about 45 degrees. And this one's different because of the scale. Now, if you have a sparse amount of features, it becomes a very complicated problem because, you know, there's a lot of solutions. There's a lot of ways that it can wiggle around. And so it's less constrained. Anyhow, thank you. Questions, comments, criticisms?